We're going to present one last set of models to represent diffusion or infection through a network. And these are in a different flavor than what we've seen with our differential equations. These are modeled a little bit more with a kind of a logic that describes how the process evolves on the network. So again, not through a differential equation, but instead through some sort of logic. And so these are called, in general, the general class of these types of models are called influence models. And so again, these can be used to model all sorts of things, a lot of the same things that we talked about for diffusion and infection spread. One of the reasons why we introduce it now is because there's some interesting and kind of intriguing connections between the late time properties of SIR model and the results of either of these independent cascade or linear threshold models. In particular, why that's interesting is because where the SIR and our diffusion models, they used a real valued state. This means that the state varied over from 0 positive values, even possibly negative values in the diffusion case. So you could have real valued states, whereas here in these influence models, these are really just binary states, so on off. And so there's some appealing aspects to that in the sense that it would be great if we could just say someone's infected or not infected. Ultimately, that's kind of what we get out of the late time properties of the SIR model. So again, that connects there. But what's interesting is we're getting similar results despite the fact that we're using a very different way to represent the state. And also the fact that we're using this logic rather than a differential equation. So we're going to describe two different versions of an influence model. So the first one's called independent cascade, and the way this works is it's very simple. So there's a set of nodes that we'll call S. Sometimes that's called a seed set, and so those are initially active at the beginning of the simulation. Then what happens is you enter the phase where any node that you just activated, so only nodes that you just activated, you attempt to activate all of their neighbors. And the key thing about this is that you only do this once. So if node U becomes active, it's got 5 neighbors, you're going to try each of those 5 neighbors, and you're only going to try them one time. And then in the next time step, that node will not have been newly activated, and so you don't try those same edges again. And so in this case, the adjacency matrix importantly includes probabilities on the edges. So in the graph itself encodes the probabilities of communicating or activating a node that is a neighbor. So again, each edge is really only tried once. Now it is possible for a node to try to activate a neighbor. It doesn't succeed, but then somehow that neighbor becomes active through another path. So that is possible. But the key thing is each edge is really only ever tried once. And so what you're going to do is you're going to take a look at this independent cascade and compare it with some of the late time properties of the SIR model. An alternative an alternative influence model is the linear threshold model. And so again, we start with an initial seed set S of nodes that are active. And so in this case, now what happens is that you take the sum of all the neighbors. So you look over all the nodes. So for node I, if all of its neighbors, the sum of all of its neighbors' state values, essentially 1 in this case if it's active and 0 if it's inactive, if that exceeds a threshold, then you activate node I. And so this is essentially the idea of peer pressure. So if you have the rest of your family using, say, Android phones, that you will be peer pressured into also using an Android phone. And this notion, again, this AIJ encodes some weights in order to inform how you sum up the neighbors. So again, these are weights that represent how each node affects each other. And it's a threshold on your neighborhood now that determines whether you become active. And so now you can try this process over and over again. There isn't this same notion that each edge is only tried once. And so what's interesting about this is that instead of there being multiple different ways, you're not flipping a coin here like you are in the independent cascade model. Here you're assigning random thresholds. And so you could assign a slightly different threshold each time and get different behavior. So the rest of the process is deterministic. So one of the fascinating things about the influence models is the fact that there's quite a bit of similarity, despite that the structure and the logic behind these two methods is quite different. The results are quite similar. So there's another example of some phenomenons that we saw back when we were talking about power law degree distributions. There were lots of different generative methods, generative random graph methods that created networks with power laws. So similarly, there's lots of different cascade or thresholding models that then would yield a very similar kind of propagation of the activity through the network. So you'll explore this a little bit more in the lab, where you compare the SIR dynamics and the late time properties specifically with one of these influence models. So eventually, when we talk about controlling systems, it's interesting to think about both SIR dynamics, where to disconnect the network or to essentially remove someone, maybe through a vaccine, application of a vaccine, in order to apply control. Here, in the context of influence models, it's interesting, oftentimes people are interested in understanding what is the initial seed set S that guarantees the most activated nodes after all. So you can imagine, where do they want to put their advertising effort in order to get the most people to buy iPhones or the most people to vote for a political candidate? And so that'll be something that we can talk about later once we think about controlling or optimizing the dynamics on these graphs.